our Elmer Racing Thor engine. That's what we're going to be talking about in this episode 6 of our er8 the tech series. So yeah, I have nothing really planned out because there's just way too much to talk about to be able to fit this into a single episode. So I'm just going to have to wing it. So yeah, if you're seeing this is take 1 and I nailed it. Otherwise, yeah, I'm going to need to think about that again. So we'll see how it goes. First of all, yeah, the whole idea with the Thor engine and what's up with that. So there are, I mean, lots of really high power engines out there. There are people that tune the legendary Toyota inline 6 engines, the 1FC engines, and lots of TB48 engines, and 4-cylinder Cosworth engines, and all kinds of different engines to really good horsepower levels for circuit racing use. And of course there are lots of V8 engines and V6s, turbocharged, normally aspirated. Then of course if you need something a little bit better, so by better here I mean more suitable for circuit racing, so a lower weight, then you start getting into some problems because there isn't really anything there in the gap. You can of course move over to, I think there are a couple of companies that make sort of motorcycle based V8 engines, for instance, so they use lots of stock components from motorcycle engines, which is really good, saves on cost, but you're not really getting a good power to weight ratio with those if you look at the stats. But yeah, if you want something better than that even, then you end up looking at like full out race engines that are like OEM engines. So Formula 1 engines typically then is the next thing to look at, and those are, I mean, of course, really good engines, but they're built to a strict regulation or set of regulations. So that means they end up being very expensive for their power to mass ratio. And I think this is, one of the things that we were looking at, that there isn't really like any super high power to mass ratio engine that has a reasonable cost. So if you look on, I think Cosworth, for instance, they have their V8 F1 engines. I'm not sure, did they even have their V10 F1 engines listed on their website for sale? Of course, you can't just call them up and buy one of them because they need to run a batch of castings and stuff like that. So when I spoke to them at some of the expos, I think they were saying that if there was some customer with some like race series setting or something like that, and they needed 15 or plus engines and the full support to run them actually at the events also. So you can't just purchase the engine, you need to have the engineers there and the support to start the engines and check all the parameters and so forth and so on. So I mean, there are of course extremely good race engines, but very expensive. So yeah, probably like multiple millions per engine, I would assume that the total cost would be for something like that. So our Thor engine is as you probably know if you've been watching these previous episodes and following the internet in general, then our Thor engine is now the highest power to mass ratio OEM circuit racing engine that has ever been built, as far as we know anyway. The previous record holder were the V10 F1 engines that were almost unregulated basically. I mean, they had displacement limitations and stuff like that brought the cost up a lot, but otherwise were pretty much weight wise unregulated, so they got a really low weight on those engines. I mean, for a naturally aspirated engine, for the rules availability, of course, or the rules restrictions. So our Thor engine, basically we started looking at, okay, how can we like get economically really good power to mass ratio. Of course, you end up very easily with a turbocharged engine, and yeah, you want to package basically the most amount of displacement that you can, but you don't want to sacrifice on RPM, because RPM is basically free power. If you increase the RPM of your engine and all the components are happy with that higher RPM, and the cylinder head flows enough, and you have a large enough valves to be able to support that flow and so forth down the line of all the components that need to work, then yeah, increasing the RPM, you immediately gain free power. So we needed to yeah, dimension all the components so that we could still get a really high RPM out of the engine. So yeah, we were looking at around yeah, so packaging wise also, what would be optimum? I think maybe a V6 or a V4 could be better, but then you end up with a completely bespoke race engine that is not really based on any engine. Or there might be some V6 engine, I'm not really sure. If you know of any V6 engines, by the way, that could use sort of as a base for a complete OEM version of that, basically, then yeah, leave some links on the description. So the yeah, demands are of course 4-valve setup, and V6 probably, yeah, typically they're 60 or 120 degrees, but for a high power to mass ratio stuff, you probably want a 120 degree one, unless of course, yeah, you just go with uneven firing setup there, so that you don't need to have a split pin crank on a narrow V. So then you, yeah, could maybe run a 60 degree or 90 degree or something like that. But yeah, so leave comments if you know of any engines to look at. So, but yeah, so for a given sort of size, because basically increasing the sort of exterior size of the engine really ends up increasing the weight a lot. So we want to fit the maximum amount of a bore size, basically, because bore size is limiting how large valves you can have, and that basically limits what kind of RPM you can, of course, in relation to the stroke also. But basically, yeah, you want to run the largest bores you can fit into your sort of given volume, and then of course, yeah, if you increase the volume a lot, then you increase the size of the pistons and the size of the valves, and then you need a higher amount of lift on the valves to be able to open the ports enough, and then that ends up requiring higher valve acceleration. So then you start at some point and ending up limiting your RPM that you can run at. So that is the trade-off on the large side. But yeah, running the maximum size of bore on a given size of sort of engine volume, you really want to push the bores as close as possible and have the least amount of stuff around the sides of the engine as possible. And of course, yeah, you really quickly end up with a reasonably high sort of bore to stroke ratio because of that. And then you could run sort of a V engine. So yeah, the crankshaft is one of the more or one of the heavier components in the engine. So the more stuff you can basically fit on the same length crankshaft, as long as you don't end up needing really heavy counterweights, then you save on mass for the crankshaft. So yeah, then if you run a V engine but you don't need to make it longer, then you can basically pack more connecting rods on the same length crankshaft, so then you end up gaining power to mass ratio. But yeah, for our Thor engine, that's inline 4, it of course allows a super tightly packaged engine bay also, which is yeah, a big requirement also. It's not useful if you have a really large engine that has a high power to mass ratio, if it's so big that it ends up compromising the aerodynamics, or you can't fit it into some vehicles that have a really narrow engine bay. So our er8, for instance, is using the chassis from Opel GT, and that has a really narrow engine bay. So if we were to run a high horsepower twin turbo V6, for instance, then that would be a tight fit to get everything in there. I mean, it would be probably doable, but yeah, turbo weight wise and packaging wise, that would be much more difficult, because yeah, then you have hot sections on both sides of the of the engines, not the engines, but on both sides of the engine, and that ends up creating some stuff to think about. Just a second. What else are we looking at? So compactness is of course important, even though it's not one of the main criteria. But that is something that our Thor engine is very, very compact. So we're able to fit that into almost any engine bay that's designed for a 4-cylinder engine. So 2-liter 4-cylinder engine, we can typically fit our Thor engine at 4-liter displacement in there. Then of course, depending on how much power you need, if you want the full 1,500 horsepower or even more for a drag racing use or something like that, then of course the turbocharger size is so big that ends up needing its own amount of space there, but it's still much more compact than running twin smaller turbos. So I mean, I think we have a really good solution for that. And it is, of course, so I mentioned the aspect that it's a OEM engine. So there are a lot of misconceptions, or maybe not misconceptions, but that people don't really grasp that, okay, this is an OEM engine, but but this is like a cast series production engine, so of course that will be better if we use that as a base. But if you start looking at stuff, if you go with cast series production engine that is produced in whatever tens of thousands or hundreds of thousands and use that as a base, then you don't have a full design sort of freedom on that engine anymore. Let's just put some background stuff on here, by the way. When you start looking at OEM solutions, so that you basically design and select all the components, or you have a single entity that designs the whole complete package, you basically have well, of course, there are more things that need to work for it to happen, because you don't have any sort of ready-made solutions or something like that the car manufacturer would have done beforehand. But then again, on the other hand, you know that there are not going to be any issues that you can't solve. So because each racing car and each team has some different things. Okay, some team might want to run a very, very high coolant temperature to reduce the size of the radiator and the amount of cooling flow they need to help with aerodynamics in some specific class where that is super critical, or you want to there are so many different things that can be super critical, like mounting the engine very, very low, and then you end up maybe having some oiling issues, or what else could I say? Some mounting angles on the engine that it needs to be mounted in some specific place, or it needs to be rigidly mounted and take up some of the torsional loads of the chassis, or there are so many different small things. And if you go with a tuned whatever Toyota, Mazda, BMW, whatever based engine, then you give up on that freedom basically. Then you're stuck with the components that the factory makes. Of course, you can always do some improvements, so add girdles to blocks and stuff like this to help out a little bit, but you're still limited by the factory components and what they can and can't do. But so with our Thor engine, I mean, we design and select all the components in-house for that. So if there is a specific race series, or the team wants to rigidly be able to take suspension loads through the engine, for instance, then okay, that's not a problem. I mean, we can look at that and see if our design is directly compatible with that or not. If it's not, it's very easy for us to do changes for that, because we do billet components on all of those, so we don't need to order a new casting set or something like that. It doesn't take 1 month or 3 months or some of these crazy time frames to get a single component redone or something like that. We can do the designs if needed very quickly, actually. And by very quickly, I mean raw material order time. So a complete or a custom redo for some specific application might take 2 or 3 weeks longer than just a direct engine that we'll have already designed. And Yeah, so one example, for instance, is the crankshaft you see here. So this is a in-house design that we designed completely also and manufacture that in-house, that allows us to do a very, very high performance crankshaft. So by high performance, I mean good durability per mass ratio, and also longevity and design-wise, like how we want to do the counterweight shapes, and how we can do the design to really minimize the mass as much as possible and look at what the natural frequencies are in relation to the engine running RPM and all of these aspects, and what kind of bearings we need to run, and are the bearings we have the best for this particular application, or do we want to run some different bearings? And in that case, we can just redesign some dimensions and suit a new customer, basically. And that is really something that if you're going with a non-OEM engine, you're basically stuck with whatever the manufacturer that manufactured the parts that you're repurposing is going to do. And yeah, I mean, you're of course performance limited also on that. So some component will be the limiting factor, and then you're stuck with that unless you start remaking that. And then at some point you end up with a solution that, okay, we remade this and we remade this part and we remade this part, but then you have all the interfaces between the different sections. So for instance, if you do you end up doing, okay, yeah, we'll just exchange the block for a billet block, for instance, but okay, that has some really thick deck height or something, because the manufacturer of that block doesn't really look at the cylinder sealing or the head gasket cylinder sealing properly, and end up just running a very thick like solid top section on that block to compensate for that. And okay, sure, you can get that to work in certain circumstances and it will be good, but then okay, yeah, then we end up running into problems with the cylinder head, and okay, then yeah, maybe we can get someone to do a billet cylinder head for drag racing applications, maybe. I think we're currently the only manufacturer that still makes billet 4-valve cylinder heads with cooling, so for circuit racing. Yeah, there might be others, I'm not sure, but I haven't heard of any at least. So there are 4-valve billet cylinder heads for drag racing without cooling, and there are 2-valve billet heads for that do have cooling also, but high performance 4-valve head with cooling, I think we're the only manufacturers at the moment. So it's not like you're going to be able to find a billet cylinder head to solve your problems for other engines, but even if you were to do that, you still have the interface between the cylinder head and the block will basically be OEM if you're like separately exchanging the parts. So have one manufacturer do a block and one manufacturer do a cylinder head, and yeah, then you're like giving up so much of the opportunities to have a better design there. So you can have much better cooling performance, much better clamping, load distribution around the cylinders and stuff like that if you design the whole package as one go. And that is basically again one of the benefits of having OEM engines, that you're not limiting yourself to some specific like interface things. Of course, it's useful to reuse existing things as much as possible, but some things are limiting factors, and then in that case you really want to do a complete redesign or look at what you actually want to use and not just what we're stuck with, basically. Let's see what I'm forgetting. Yeah, probably so I let's see how far along we are. 33. Ooh, this is a really long video already. Okay, well, it's an interesting topic also, so should be good maybe. But yeah, I think the power to mass ratio is really one of the important things to look at also. So yeah, a little more deeper into that. So our Thor engine is dimension-wise, so bore spacing and some of the exterior dimensions, and the valve layout is reasonably similar to the Porsche 968 engine, and that's cast aluminum engine designed by Porsche for the 924, I think, that they then update a little bit to the 944, and then for the 968. And so yeah, in comparison to those components, so our block, for instance, is lighter weight than that. We've pulled the weight off of the crankshaft. Our cylinder head is also lighter weight. So even with adding the vibration damper that we have on that, because the more power you have, you end up with these torsional vibrations in the crankshaft, because you have movement in everything because of load. It's just a question of how much movement there is. And you don't want to transmit too much of that through the drivetrain, because you end up breaking gearboxes, and you have problems with the clutch grabbing and stuff like that. So you want to smooth that out as much as possible, and that will also help your oil pump live longer and so forth. So even adding the vibration damper on the front, our engine is still lighter weight than the Porsche 968 original engine, which actually, I mean, Porsche did a really good job designing that. They have some really thin wall thicknesses in there, and really good design to keep the rigidity high with all of that. But of course, we have some good ribbing and design there. We can see the block milling here. So we do this in-house also. We do the design and the manufacturing in-house to be able to do the design to take the manufacturing process into account, so we can really cut down on the weight, while at the same time we know exactly how the machines work that are actually going to remove all that mass from the raw aluminum block. So that really helps us to not just make a super lightweight engine, but also keep it at a very reasonable cost. So it is, of course, a reasonably expensive engine compared to if you do some tuned like Toyota or BMW engine or whatever. But that again is not an OEM solution, and this is OEM solution. So compared to OEM solutions, we have a very good ratio. So we basically produce more power than the qualifying turbo F1 engines produced probably around the same amount of power that we recommend for our circuit racing version of the Thor engine. But those engines were actually really heavy with all the extra components and stuff like that, so not a very good comparison. But the V10 engines, so they were running, I think, around 1,000 horsepower, maybe even above that, and they were really lightweight. So they had a sort of similar, but we're at a slightly better power to mass ratio than even the V10 F1 engines had back in the time. And of course, our price for a complete engine is like under a tenth or something like that. So technology has really pushed forward and enabled us to really make a much sort of better complete package than what was available then. And of course, I mean, the rules help a lot also. So F1 engines were limited by really heavy rule use, and we basically have an unlimited engine that has almost no rules at all. It's just for racing categories that require the engine be based off some high volume series production engine. And so our Thor engine is definitely based on that. And for instance, in a World Time Attack, that rule is there to prevent people from using F1 engines, because then you end up with someone spending 1 million plus or something, and then you can't really like these single or three-person team guys can't compete anymore in any way. So it's very good to have the regulations very open. And I'm back. So now that we have a Thor engine that is a really high power to mass ratio setup, so that basically helps us with this eliminating mass section, and that means we can get the maximum amount of performance out of our high downforce race car that we have, that is otherwise as lightweight as possible. Because the engine has been one of the biggest problems. So there are some racing categories where you see really lightweight cars, but then if you want really high horsepower, then you end up with an engine that is so heavy that negates like most of the benefit of having a really lightweight car. If you have like a car that is 1,000 kilos or something like that, and you want to run 1,000 plus horsepower in it, then typically you would end up with a complete engine package that is like 200 plus kilos, 250, even maybe 300 kilos or something like that, and that would make it really difficult to get a car to 1,000 kilos. Or even if you have a car at 1,000 kilos with that engine, using a Thor engine instead will save you 150 to if you have a super lightweight engine, then maybe save you 50 kilos or something like that. But if you have a high downforce on that car, then saving 50 kilos even is going to be huge for performance. So that is really good. We have a interview from, what is this? Is this from 2017 World Time Attack? Yeah. So the first year that the Thor engine was supposed to run in the RP968, we designed and developed that with a really short time frame. But the team that was assembling that ran into some issues with the size of the oil pump that they had selected for that engine, and couldn't get the oil pressure that they wanted for that. We do have a really good sort of oil routing through the crankshaft to be able to run at reasonably low oil pressure and still get oiling for the connecting rod bearings. But the team wasn't happy with that, and of course, the team decides what they want to do. So they ended up going back to their last year's engine, and we had our engine there on show at the World Time Attack event instead. So basically the enabler of this whole project was Rod Pobestek from the RP968 team. So I mean the Rod Pobestek, that is the RP in the RP968. So he's the team boss, and he makes everything happen and does all the decisions and all the financing and everything for that whole team. So without him, I mean, this would have been a completely impossible project to do, because having a paying customer, okay, that was for components, and they did assembly work themselves, and it was a development engine, so they were not paying anywhere near a sort of list price for a complete engine. But even so, I mean, having actual customer car to go through and look at the specifications, and okay, we're at the same time thinking about how do we make this applicable to as many other race cars as possible, and how to make this as easy to do design changes for potential other customers as possible. Really helped get this project on the way, and super happy about that. And when they finally ran that in 2018, and won the world championship with that in the first go with the Thor engine, was absolutely super. So that was a really excellent event, and we were able to basically design a complete OEM engine from almost scratch, and manufacture that in between sort of 6 to 8 months, really. Okay, those were some really long months because we were putting in a lot of hours on that. But I mean, time frame wise, that is completely unheard of. So the F1 engines, for instance, where they develop those, I think those are like several year projects with these huge teams of people. Of course, they have much more stringent rules, so it's not a fair comparison. But price wise, I mean, it is definitely so. We can do that very quickly with a really small team, so we can have a very good price and extremely competitive in relation to other OEM engines. I think this has probably gone on quite a lot, and there's so much more to talk about, and so many stories about the development and how we ended up with what camshafts, and why the crankshaft is designed in some specific way, and what connecting rods we're using, and what the oil pump is, and all of these details. But that would probably take like a 10-part series or something like that to go through all the details on the Thor engine. Is for the er8 focus aspect, that's not really feasible to do so. But if there is interest in going through all of this, I mean, of course, some things like the cooling solution, for instance, is a very closely guarded secret. So we're not going to be divulging any secrets on that. But there are a lot of aspects that are completely ordinary and everyday. Well, maybe slightly bad choices of words, because it is a yeah, highest power to mass ratio OEM engine ever. So maybe not ordinary, but not sort of super innovative or anything like that. So I mean, I'm happy to discuss that and give out details. So if you guys want to see more on that, then yeah, feel free to leave comments and share, especially Facebook, Twitter, of course on YouTube also. Leave comments and yeah, specifically what you would want to see. So, but yeah, doing these videos, it doesn't take that much time, but it does take some time, and all of that time is away from developing stuff further. So yeah, but it's up to you guys. If enough of you people want to check that out, and you're happy to share it with your friends and stuff, then yeah, maybe we'll revisit the Thor aspect when we're done with this er8 series. But yeah, I think that's a wrap for this. So I'm Oscar from Elmer Racing, and this was episode 6 of our er8 the Tech series, focusing on our Thor engine. See you guys in the next one. Bye.